In section 7.6, we're going to be looking at function operations, including addition, subtraction, multiplication, and division of functions, as well as finding the composite of two functions. Okay, so we're going to start by looking at the actual operations of functions, which is just what it says, our basic four operations: addition, subtraction, multiplication, and division of functions. And although the combining of the functions through these operations isn't all that terribly complicated, at this point, what's really going to be our focus is a matter of the domain of these different functions. Now, depending on the original functions themselves is going to affect our domain, but in particular down here on the division functions, where we're dividing two separate functions, we remember that division, we have an undefined place where if you divide by 0, that's undefined. So we want to make sure that we pay special close attention to this denominator here, this function in the denominator, and what makes that particular function equal 0. That's going to be a big key to our domain when we talk about our functions and their domains. Okay, so let's look at a few examples. We'll start with some addition and subtraction. Now, one thing that you want to remember, we did function notation earlier. If you remember, function notation like this is read f of x. This does not indicate any multiplication between these two variables. It's just simply a name for this function that replaces my normal y that would go here for my dependent variable. So I have two different functions. Naming one of them f and one of them g allows me to tell you to do something to those two equations without necessarily having to write out the entire function every time I'm talking about it. Okay, so as well as other things it'll tell you, but for now, that's the main purpose that we have here. So what I'm going to do to these two functions, first of all, is it says that it wants me to add the two functions together. So I'm just going to be adding 3x plus 8 and 2x minus 12. And like I said, the actual operation of adding these together is not all that entirely difficult. So to do f plus g, I'm going to take function f, which happens to be 3x plus 8. So let's do that, 3x plus 8. And I like to keep my functions in parentheses until I'm sure what I'm actually going to be adding or subtracting. And then the second one is 2x minus 12. And so when I put those together to get f plus g of x, combine my like terms. Since it's all addition, I just can combine my like terms. So 3x plus 2x gives me a 5x, and a positive 8 and a negative 12 are going to give me a minus 4. So my function f plus g of x is 5x minus 4. Now, if you move down to the next addition example I have, which is g plus f, you'll notice that on g plus f, it's still addition. So the same rules are still going to apply. When I flip them around and do 2x minus 12 first, and then plus 3x plus 8, you'll notice that I get exactly the same answer that I had before. So for g plus f of x, I'm going to end up with, again, 5x minus 4. So it really, the addition part is commutative just like normal when you do addition problems. Oops, sorry about that there. Okay, so let's go back here. Now let's look at subtraction. And in subtraction, same thing, f minus g. So my function f is 3x plus 8. And then my function g, so minus g, is 2x minus 12. Now this one I have to be a little more careful because I do have that negative sign in the middle. So when I combine like terms, 3x, I distribute the negative, makes that minus 2x. 3x minus 2x, let's do this, f minus g of x. 3x minus 2x leaves me with just x. And then secondly, 8, distribute a negative, minus negative 12, actually ends up being 8 plus 12, which is plus 16. So f minus g of x is x plus 16. Now, g minus f, if you think about subtraction not being commutative, so I'm actually going to have to do the subtraction. Starting with g, which is 2x minus 12. And then I'm going to subtract f, which is 3x plus 8. And again, being careful to do my distributing correctly with my negative sign here in the middle. 2x minus 3x is going to give me a negative 1x, or negative x. So g minus f starts with a negative x, and negative 12 minus 8 is going to give me a minus 16. Now you'll notice it's the opposite of what I just did, which g minus f is the opposite of f minus g. Okay, so it does give me the opposite answer by switching those two around. Okay, now as far as, well, let me skip back to that just for a second. As far as the domain goes, because all of my functions here are all linear functions, and I know that linear functions have all real numbers as their domain, the domain of these functions will always be all real numbers. Because I started with linear functions, I still have linear functions. No matter what I put in for my x, I can put in any real number, and that's going to still give me a function. Okay, so now, if let's not skip to composite yet here. If I go to multiplying and dividing, again, I'm just going to do exactly what it says. So it says f times g of x. If my function f of x happens to be x squared minus 1, and my function g is x plus 1, I look at these operations and I see two binomials, and two binomials tells me from the past that I need to do FOIL. So I'm going to be using FOIL to multiply these two things together. So x squared times x. So let's go f times g of x, and I get x squared times x is x cubed. Then I get x squared times 1 is plus x squared. Then I get negative 1 times x is going to be minus x. And negative 1 times 1 is negative 1. Now I would check this since I did FOIL, make sure there's no like terms to combine together. But my final answer then is x cubed plus x squared minus x minus 1. Now, as far as the domain goes, if you look at your original two functions up here, this has a domain of all real numbers. This has a domain of all real numbers. When I put them together and I multiply them, this polynomial has a domain of all real numbers. And again, remember, when I think domain, I think of, is there anything that I couldn't be doing here? And there isn't. I mean, there isn't a real number that you could not put into that problem and get a real number as an answer. So your domain is all real numbers, which then makes the next one very easy. Okay, because this one down here, g times f is going to be exactly the same as f times g. So I won't go through the process of re-multiplying that out for you. But again, since multiplication is commutative, g times f, f times g, same answer. Now division, not so much. Division doesn't work that way, right? It's not commutative. So if I'm going to do f divided by g, I'm going to start with x squared minus 1 over g, which is x plus 1. Now, in this case, I want to do two things. My numerator, x squared minus 1, does factor. And when I factor it out, you'll notice that it creates a common factor with the denominator. So my x plus 1's end up canceling out, and I get f divided by g of x equals x minus 1. Now, the one thing about this, when you consider your domain, is you have to consider the original problem up here. And remember I said, now we talked about just a bit ago that these two things, their domains are normally all real numbers. However, once you put x plus 1 in the denominator, this causes a problem for my function, because having a denominator means there's a possibility of getting a 0. And if I get a 0, that division is undefined. So what I want to know is what makes x plus 1 equal 0. And in my case, that would be negative 1. So as far as the domain goes, I want to make sure that I say that x cannot equal negative 1. It can be any other number, any other real number except for negative 1, because negative 1 would give me division of 0, and division of 0 is undefined, making that no longer a function. Now for g over f, this time the x plus 1 goes in the numerator and the x squared minus 1 goes in the denominator. But again, the process here still is the same. I factor the denominator this time, causing the x plus 1's to cancel, and I end up with g over f of x being 1 over x minus 1. Now again, there's a domain restriction or a value or values that we can't use here. And since my original denominator actually had two things in it, the two things that make this 0 would be a -1, like last time, as well as a +1. So I actually have two things that I can't use in my domain this time, a +1 and a -1. Okay, now the last thing we want to look at is a composite function. And a composite function is when you want to combine two functions together. It says by using the range of the first equation as the domain for the second function, right? So if you had two different situations where one function determined one value and then you needed that value to determine in the next equation, you could put those functions together and make one single composite function. Okay, so we're going to start out pretty basic. We have two functions here. We're going to do f of x is x minus 2, and g of x is x squared. So according to this, we're going to put always the second function in our composite notation here into the first. So I'm going to put f into g, and it's just like the substitution method. So I'm going to substitute x minus 2 into the function x squared. So what I end up with here, if I substitute x minus 2 into that function, is normally this would have said x squared, and I'm going to substitute the function x minus 2. So I get this, x minus 2 quantity squared, which we know we do FOIL. We multiply that out by FOIL, so x minus 2 and x minus 2. And I'll end up with g composite f of x, which equals x squared minus 4x plus 4 when I'm finished with my FOIL. Okay, now over here, it wants me to use g composite f to evaluate the value of -5. So I simply need to take -5 and substitute that into my function. So this is going to be -5 squared minus 4 times -5 plus 4. And you can either do this by hand or you can calculate this with the calculator. But either way, you're going to end up with a total calculation here of 20. No, let me try that again. How about 49? Okay, -5 squared is 25, -4 times 5 is 20, 25 and 20 is 45, and 4 is 49. Okay, so the second composite function, we're just simply going to reverse the process, only this time g is going to go into the function f. So this one actually makes it a lot simpler. When we take the x squared and we substitute it for the x in this equation, it just simply makes the equation x squared minus 2. Much simpler to calculate, no FOIL, no multiplying. And then secondly, if I want to do f of composite g of -5, then it just becomes -5 squared minus 2, which is 25 minus 2, which is 23. Okay, so that one is a little bit easier to calculate, a little bit easier to do the composite, but it's just really a matter of substitution is all it is.